Welcome back. Now we are going to talk about the first component we said about statistics is variability. This module is now going to concentrate on how to actually measure this variability. So let's go back to our example where we had the 13 FEV1 numbers. So there they are, 2.3, 2.15, etc. And we've got 13 of these. Now, we said that their center can be nicely given by the mean, which in this case is 2.95. Now, so we know where these things are centered, and now we'd like to get an idea of how they vary around that center. So let's center every single observation by subtracting the 2.95 from every observation. And there it is. So the 2.30 is minus 0.65. That's minus sign because it's to the left, and the magnitude is 0.65. And the next one is minus 0.8, and the next one is 3.5, which is to the right-hand side of 2.95, so it's a plus sign when we subtract 2.95 from 3.50. So there we have it. So this blue column here gives us the deviations from the mean for each observation. All right? So this is going to give us an idea of how these things vary around the mean. So how do we summarize this? Well, why not take the mean of these? Just like we did before, we summarized quantities by taking their mean. We could, but if we did, we would run into problems because the mean of these so-called residuals is always 0. That's from the definition of what the mean is. It's the center of gravity. So that's why these things are always 0. So the plus signs, the value of the pluses cancel out the negatives, and we always have 0. So the mean is always going to be 0, not very informative. So the problem, as I said, it's the pluses knocking out the minuses. So what can we do? Well, one thing we could do is get rid of the signs. So take the absolute values. And that is called the mean absolute deviation. If we take the average of that, we're not going to do that today. What we're going to do is the other favorite way of getting rid of the signs, and that's by squaring. So if we square each one of these things, now we see all of these numbers here, all of these numbers down here are all positive. So now what we can do is take the average of these. So take this sum, there's the sum is 4.66, and average that out, and that will give us the average of the squared deviations. We call that the variance. So the sum of the squared deviations then averaged out. Now you'll notice that I used n minus 1 and not n, but I'll tell you in a couple of lectures, in a couple more visits why we did the n minus 1. But for the moment, just trust me. So we averaged out, and we call that the variance. So we averaged out by n minus 1 as opposed to n, and we're not going to get into trouble unless we have one observation, if n is 1. So in which case, we can't do anything anyway. We can't judge variation from a single observation. So anyway, that's defined to be the variance. All right, so each one of these deviations is squared. So when we take their sum, that's going to be a positive quantity. And so the variance is always greater than or equal to 0. So the average of positive quantities is going to be positive, and so the quantity is always going to be greater than or equal to 0. In fact, if we look at this closely, the only time this can ever be 0 is if each one of these quantities is 0, which means each one of the x's has to be equal to x bar. In other words, if there's no variability, only then would this be actually 0. So the variance equals 0 means you have no variability. So let's apply that to our FEV1 numbers. And first let me clean it up so you can see what's going on. Okay, So let's apply that to each one of our FEV numbers, and we get that their sum, remember, was 4.66, divide by 12, because there were 13 numbers, and we get 0.39 liters squared. We squared the quantity. The x's were in liters, the mean therefore was in liters, and when we square it, we're now talking about liters squared. So this is unfortunate. We're not really interested in liters squared. We're interested in liters. So what we can do is reverse this operation of taking the square by taking the square root. And that is called the standard deviation. So the standard deviation is the square root of the variance, and we take the positive square root by convention. So in our example here, there is the positive square root is 0.39. I'm sorry, the positive square root of 0.39 is 0.62 liters. So there is the standard deviation of these 13 numbers. That's it by definition. Let's apply this to the first 10 variables in our Framingham Heart Study data, and there they are. When I ask for summary in Stata, I also get the mean, the standard deviation, and the min and the max of each one of the observations.